All right, what we're going to do is look at derivative rules for trig functions and some relationships that they have. Some of them are really tricky, some of them are really easy. All of them you'll need to memorize. And you'll use them so much that they should stick in your brain anyway. It shouldn't be too tough to be able to do all this. But first, let's go ahead and look at the derivative of the sine, but let's look at the limit rule. So we're going to take that whole limit rule where we would let let's see, we don't want that guy, we want this guy. The limit as h approaches 0 of f of x plus h minus f of x all over h. Now, we're not going to have to do this every time, but I just want to use it this once to show us what's going on here. And so if we're looking with the sine of x, then what we're going to do is we're going to look at the sine of x plus h and the sine of x. Those are my two functions that I'm going to be working with. So how is this going to shape up? Well, we're going to look at the limit as h approaches 0 of sine of x plus h minus the sine of x all over h. And remember, we're wanting to find a place where we can get the h in the numerator and the denominator to divide out, or where we can rewrite this in a way that allows us to use that h. But right now, if I substitute in a 0 everywhere, I get 0 in the denominator, and that's not going to work. So you might remember a trig function, sine of an angle plus an angle, the sum and difference stuff. And so we can actually rewrite the sine of h as the sine of a, let's see, sine x cosine h plus cosine x sine h. And then we're going to finish that off with a minus sine x. Okay. All this is over h. Well, I still have that h in the denominator that I can't get rid of. So I have to think of a way that maybe I can do that. Well, check this out. What we're going to do is we're going to take these two guys right here and this guy right here. And the cool trick that I'm going to do is I'm going to factor a sine x out of that. So we're going to have the limit as h approaches 0. And just I'm factoring out of only the green. So I'm going to have sine x times cosine h minus 1 minus cosine x sine h all over h. Okay, you with me on that? And then what I'm going to do is break this up into, oops, this should be a plus. I'm going to break this up into two pieces, because with that addition symbol in here, I actually can work with sine x cosine h minus 1 over h, and I can work with cosine x sine h over h, and I can do a plus, and I can work with each one of these guys independently now. Okay, so so this gets it quite a bit more manageable because now I've got little small chunks to work with. And so let's just carry this on right up here. If you'll look on that very first guy, I can actually take the sine of h and put him in the front, and that just leaves me, or the sine of x and put him in the front. That just leaves me with cosine h's in the middle. Same with this guy. I can take him and put him in the front. And so what I end up with is sine x times the limit as h approaches 0 of cosine h minus 1 over h plus cosine x times the limit of sine h over h. Running out of room. Sine h over h. Okay. All right, not a big deal. Not a big deal. The cool thing is this. We can actually look now at some limit rules that are going on here on your calculator. So if you graph and look at your calculator, this guy right here, cosine of h minus 1 over h. If you graph that guy and look at what's happening as h approaches 0, the function actually has a limit of 0. So this will be sine x times 0 plus. And then we've talked previously about the graph of this guy as he goes to 0, sine h over h. As h goes to 0, that guy is just a 1. So we're going to end up with cosine x times 1. And sine x's go away. And so the derivative, based on our limit, is cosine x. So this is kind of a long drawn out process. I probably am not going to ask you to do it again. But really important is to be able to understand that when I have the graph of something, I can look at that and determine what the limit is. And then I can use it to help me figure out other things. So in the long run, the important part is this guy right here. The derivative of the sine of x is cosine x. All right, so here are some derivative rules that you need to make sure that you have written down that involve the different trig functions. So sine x, cosine x we saw. The derivative of the cosine x is negative sine x, and the derivative of the tangent of x is secant squared x. So you will use those three quite a bit and probably have them committed to memory fairly quickly just through your work. The other three are the cosecant of x, and the derivative of that is negative cosecant x cotan x, the derivative of the secant of x, which is secant x tan x, and the derivative of the cotangent x, which is negative cosecant squared x. Those are a little bit trickier to get sorted out in the brain at times. So just work with these guys, practice these guys, have them written down so that you can see what's going on. And before you know it, you'll have them memorized, okay? So how can we use these things? Well, let's work out a couple of examples. First off, we've got x squared times sine x. This is a classic product rule problem. And so what we need to look at is we need to look at this guy as a u and a v. So when I look at this guy, I need the derivative of u, which is 2x, and I need the derivative of v. So the derivative of sine x, I just look up here, the derivative of sine x is cosine x. So when I solve this problem out, I'm going to take the first function times the derivative of the second. So y prime is equal to the first function times the derivative of the second, plus the second function times the derivative of the first. So when you put all of this together for one problem and an answer, the derivative is just going to be y prime equals x squared cosine x plus 2x sine x. And there's really not much else we can do with that. We're done. We're done there. Okay. I'm going to move this quotient rule guy up. So let me just grab him and move him up real quick. We'll work him up here. We've got a little bit more room. So I'm going to go with low d high. So u prime is equal to low D high, well, derivative of cosine. Look over here, derivative of cosine, negative sign. Minus high, D low, well, derivative of 1 is 0. Derivative of sine is cosine. So negative cosine x. All over 1 minus sine x squared. Okay, so this looks really crazy. What do we got? Well, on top I have 1 plus sine x squared, sine squared x, plus cosine squared x. Actually, that shouldn't be a 1, that should be a minus sine x. Let me just give myself room here. All right, looks like this. And if you'll remember back to the glory days of trig, we loved anything that showed up as cosine squared x plus sine squared x, because that whole thing goes to 1. And so what I'm really working with is 1 minus sine x over 1 minus sine x squared. And if I have the same thing on the top and the bottom of a fraction, I can cancel it out. So 1 minus sine x cancels one of those guys out. And my overall derivative then becomes 1 over 1 minus sine x. You will need to pay attention to some of your trig rules. You'll need to use some trig identities on occasion, but a lot of these problems will simplify down a little bit with just a little bit of effort and a little bit of algebra. Okay, here we've got the classic hanging spring problem. So a weight hanging from a spring is stretched 5 units beyond its rest position and released to bob up and down. Its position at any time t is s equals 5 cosine t. What are the velocity and acceleration at time t? Describe its motion. So they're telling us the position is the s. So we just take from that s, our position, as s equals 5 cosine t. So velocity is the derivative of position. So velocity then is going to be 5, and then times the derivative of the cosine, which is negative sine t. So velocity is going to be negative 5 sine t. And then acceleration is the derivative of velocity. Okay, so acceleration is equal to negative 5 times the derivative of the sine, which is the cosine. Okay, so here is your position function, velocity function, acceleration function. And so what does this tell us about the motion? Well, the position is 5 cosine t, so position is going to look something like, this may not be super exact, but it's going to look something like this. Cosine, we're going to start up here at 5. We're going to go down here to negative 5. It's a cosine function. So it looks something like this. And then what we're going to do is we can graph the velocity from that. So we'll do velocity in this pink color, and it's the sine now, but it follows right along with the cosine. So it's going to have this sort of shape. Again, that might not be 100% exact, but it's going to be very close. So here's my velocity. It's a negative velocity, then positive, and then negative again. And then just remember with the with our spring, what we're doing is we've got this weight, some weight, and we've stretched the weight on a spring to 5 units off of its normal. So we would say if this would be 0, this would be up 5. Here we are at -5. Okay, so this weight is going to bounce up and down. All right, and it gives us then all these things. So we can look at these two graphs and determine all kinds of different things. It's got its maximum velocity, when that weight is up here at 5. So when it's zipping back up, it's at its maximum velocity. It's at its lowest velocity when it's on its way down. And so we can just put all of that together to kind of get an idea of what's going on. The speed of the weight is always the absolute value of the velocity. So if we wanted to know what the speed of the weight was at any time, we can just pick that time interval out, place it into t, and take the absolute value. When t is 0, the speed of the weight is 0, and as the weight reaches its different maximum points, it freezes before it changes direction. So at those times with it's freezing, it's going to have no speed or velocity at all. The acceleration is always the exact opposite of position, okay, because you're the way that you would move. So when the weight is above the rest position, the gravity is going to pull your weight back down. And when the weight is below rest position, the spring is going to pull it back up. So all these things are happening on this one problem. And what's the biggest thing? The biggest thing is if I asked you what the position was, or velocity, or acceleration at a specific time, you could tell me that by substituting in whatever value we are interested in right here for t. And then we would know what our position, velocity, or speed. All right, so we know that if we start with position, take derivative, we have velocity. If we take derivative velocity, we have acceleration. But there's another derivative we can look at that's related to all of those, and it's the third derivative from the position function, which is the derivative right under acceleration. It's called a jerk. And a jerk is a sudden change in the acceleration. The jerk is what spills your coffee drink or your tea drink or your Coke or Sonic or whatever. A jerk is what spills the drink in your car, all right? And that's what the third derivative of a function is called. It's called a jerk. So one of the things that's just kind of fun to look at is how a jerk works. And so if you think about gravity, okay, gravity has a constant acceleration of -32 feet per second squared. What about if we took the derivative of that? Now remember, that is acceleration. So if I take this acceleration function right here of -32 feet per second squared, and I look at the derivative of that, I get 0 feet per second squared. Well, what does that mean? It just simply means that there's not a lot of bumpiness going on while we're sitting still on the earth. There's not a lot of bumpiness going on when you're falling. I know sometimes friction, but if we just looked at the falling of an object and only based it on the acceleration of gravity, it's not going to suddenly jerk around and change directions. Everything is smooth. Your book really says it best. I'm going to look at your book here. This explains why we don't experience motion sickness while just sitting around. Imagine being stuck in your desk all the time, and as you're sitting in your desk, you're bouncing or changing direction. that could be pretty brutal, okay? But because the acceleration of gravity is 32 feet per second and not some fancy equation, when you take the derivative of that, you get 0 for your jerk. And it wouldn't be feet per second squared. I think it'd be feet per second cubed. I'll have to look that one up now. Now I've got myself confused. So anyway, I'm going to erase this guy. But our jerk, in any case, would be 0. So what is the jerk of the previous simple harmonic motion problem? And what does that mean? Well, that previous simple harmonic motion problem, if we look at it, if we can go back to it, we were looking at an acceleration that said -5 cosine t. So if we look at the derivative of that, we would end up with -5 times the derivative of cosine, which is 5 sine t, and so that would be the jerk function for your simple harmonic motion problem. What does that mean? Well, it just tells us when we're going to have that change of direction because of the acceleration. You know, when our acceleration has that sudden change in direction, and it only doesn't occur at the extremes of the displacement. Okay, so in other words, when you are at your widest points, it's not changing, but when the acceleration changes from the rest, that's where you're going to have this jerk in this change in direction. So there's your jerk rule, third derivative, kind of fun thing to look at. All right, so we want to find the equations for lines that are tangent and normal to the graph of f of x equals tan x over x when x is equal to 2. What does that mean if we're going to find lines that are tangent or normal? All that means is we've got to have a derivative, and we need a point. And if we have a derivative and a point, we have a slope. So let's go ahead and try and figure out what the derivative of this guy is. We're going to have to use the quotient rule. So f prime of x. And when we do this, we need to know what the derivative of tangent is. What's the derivative of tangent? And that's going to be secant squared x. So I'm going to have low d high minus high d low all over low. Okay? And on the top, I'm going to end up with x secant squared x minus tan x over x squared. This is my derivative of my original function. And so I can also find the slope. Where am I interested at slope on this particular guy? I'm interested at slope when x equals 2. So in your calculator now, you're going to have to do a little bit of work. And what we're going to do is we're going to put a 2 in to all of these different places. Okay? And what we're going to find is that our y value, not our y value, our slope in this case, our slope is going to be 3.43. All right, and that's okay. We can have that. It's not a problem at all, and we're dealing with the trig function too, so that's probably going to give us a decimal anyway. So what does that mean though? Well, I need to know a point that is on my curve. Okay, and so when you put your 2 in for x into your original function, you would have the point tangent 2 over 2. And so if I'm going to write the point slope form of that, so when you punch that into your calculator, the decimal form of that would be 2, and then the y coordinate would be negative 1.09. 2 or 3, depending on how you round. So my tangent, we'll write tangent in purple, my tangent line is going to be y minus the y coordinate equals the slope times x minus the x coordinate. And this is a good answer. You don't have to do anything else here. It's a point slope form of a line. I'm happy. Remember, with normal, that's going to be the perpendicular. That's going to be perpendicular to the slope. So that's going to be the opposite reciprocal. So when I look at the opposite reciprocal, I get 0.291. So our normal then is going to be y plus 1, 0.093 equals 0.29, negative 0.29, x minus 2. So there's how you can find the tangent and the normal using your trig functions and derivatives. It's no different than how we were doing it before. It just may have a little more decimal action going on. Okay. What about if we wanted to find the second derivative, though, of secant? Second derivative of secant. Well, we just dive right on in. We need the first derivative. So the first derivative of secant is secant x tan x. And then once you get here, you've got u and you've got v. So I need the derivative of u prime. Well, we just talked about that. Derivative of secant x is secant x tan x. And we need the derivative of v. So when you look at the tangent, the derivative of the tangent is secant squared. Secant squared x. So we're going to go with the first times the derivative of the second. So we're going to have secant x, and this is going to be y double prime here. We're going to have the first secant x times the derivative of the second, secant x tan x, plus the second, which is just going to be tan x, up. I've gone wacky here. The first, which is secant x, times the derivative of the second, which is secant squared x, plus the second, which is tan x, times the derivative of the first, which is secant x tan x. Okay? And so when you simplify this all the way down, you're going to end up with secant cubed x plus tan squared x secant x. And this is a good answer. You don't need to stress yourself out and try and simplify that down a lot more either. So there you go, some examples of trig functions and how to use them. Looking also at previous examples, which included jerk and how to derive some of these things in simple harmonic motion. A lot of stuff going on here. So make sure you've got good notes that you could go back and refer to. Make sure you ask questions or send a tweet to @HazelwoodMath.